All right, welcome back to more discussion about vectors. Today we're going to talk about another type of vector multiplication. This one's called a dot product. So we have more vector multiplication, and with our dot product we're going to talk about defining parallel and perpendicular. And of course, if it's not parallel or perpendicular, there should be an angle between the vectors, which we will have a formula and we'll be able to calculate that angle. All right, quick review. Scalar multiplication, making a vector shorter or longer simply by putting a number out in front, changing the scale of the vector. So if I have a vector 3, 4, we of course know the magnitude of that vector is 5, but I can make it longer by putting a number out in front. That would give us 9, 12. These two vectors have the same direction. Here's 3, 4. Here's 9, 12. The direction has not changed. This vector is just 3 times as long as the original. All right, we have a new definition today. It's called a dot product. Okay, this is what it looks like with variables. I think you'll find that in practice, it's really quite simple. We're going to pull our vectors apart and we're going to multiply each of the elements together. So in this case, example number 1, if I want to take 8, negative 3 and dot it with 2, 5, we're going to multiply 8 times 2. And then we're going to multiply negative 3 times 5. And then we're going to add those together. And that is a dot product. We should note the very interesting thing here that I'm starting with two vectors, and when I do their dot product, I'm ending up with a number that is not a vector. Kind of interesting. Don't know if you've seen that before. Anyway, dot product works across dimensions. So 3 times 5 is 15. Negative 1 times 5 is negative 5. Negative 4 times negative 2 is 8, and we can very simply add these together and get a dot product of 18. So it's a nice, useful definition for us. It's going to give us all sorts of stuff to do when we get to 3 space. All right, so now let's take a look at why we did those two definitions specifically. Okay, first of all, we're going to define parallel vectors. Parallel vectors are vectors that are scalar multiples of each other. So in the example that I had previously done, 3, 4 is parallel to 9, 12. How do I know this? Well, 3, 4 has been multiplied by 3 to give us 9, 12. Okay? For those of you that like to save paper and be as concise as possible, there's a really cool symbolic version of this. The vector u is parallel to the vector v if and only if the vector u is a scalar multiple of the vector v. And that's how we write it. Same definition in math symbols. Let's take a look at proving two vectors are parallel. Okay, if I want to verify or prove that two vectors are parallel, you are going to fill in the blank. Okay, don't talk to me about their scalar multiples or worry about any of that. If you want to prove that they're parallel, all you have to do is fill in this blank. Now there's a nice way to go about this. 21, 35, 15, 25. Let's see, do those, first of all, are they equal? And what do I get when I reduce them? This is, everything here reduces to 7/5. I think that's upside down because if I multiply this by 7/5, it's getting bigger. What if I multiply it by 5/7? Will that create what I want? 21 times 5/7 is 15, and 35 times 5/7 is 25. You have just proven that those two vectors are indeed parallel. All right, now we have our definition of perpendicular, and I'm going to start using this word orthogonal. The book's going to use it. It's a little bit more powerful than perpendicular. We'll explain that later. But orthogonal basically means we're perpendicular in n-dimensional space. So we're going to be perpendicular in 3 space or 4 space or 5 space. So you'll start seeing the word orthogonal. So two vectors are orthogonal if and only if u dot v equals 0. Now we talked about a dot product already. So if I take the dot product of the two vectors and I get 0, that tells me that the two vectors are indeed orthogonal. Those of you wanting to save on paper, u is orthogonal to v if and only if the vector u dot the vector v equals 0. And that's how we would write this in mathematical symbols. Let's take a look at some examples here. How can I verify or prove that 1525 is orthogonal to negative 10.6? Seems pretty straightforward. 1525 dot negative 10.6. And crazy thing happens when I do this. Negative 150, positive 150, and lo and behold, 0. We have just proven that those two vectors are indeed orthogonal. They're also going to give you some questions on the homework that might look something like this. If 27 is orthogonal to negative 5k, find k. Okay, what does it mean to be orthogonal? That means that the dot product has to be 0. Let's see what we got when we do our dot product. Here's negative 10. Here's 7k. And when I add those together, I must get 0. So that tells me that 7k must equal 10. And if I plug in the k of 10/7, I would get an orthogonal vector. Now, sometimes they're not as limiting as this. They're not going to give you a starting point. They're just going to ask you to find a vector that's orthogonal. Okay? In 2 space, we have a bit of a trick here. It's pretty simple. I can simply switch these two, negative 4 and 8, and then I have to change one of them, change the sign on either one. I can change the negative 4 to positive 4, or I can change the positive 8 to negative 8, but don't do both. So in this case, I'm going to make it positive 4. And let's take a look at why that works, because now 8 times 4 is positive 32, and negative 4 times 8 is negative 32. So when I add those together, of course, I get 0. For those of you who remember algebra, if I had a slope of negative 4/8, how could I find a perpendicular slope? If memory serves, I'm pretty sure I take the negative reciprocal. Don't I switch these up and down and add a negative? Switch these back and forth and add a negative? Very similar. Okay, in 3 space, we can use a similar trick, but since I have 3 of these, I'm going to switch 2 of them, and the third one becomes a 0. Okay? So, 12, whoops, forgot to negate one of them. Negative 12, 0. That gives me the 0 that I want. So every year I get students that ask me, well, what if I just take 0, 0, 0? Wouldn't that be orthogonal? Well, yes, 0, 0, 0 technically is orthogonal to every vector, because when I do a dot product with 0, 0, 0, I always get 0. The problem is it also happens to be parallel to every vector, because I could take 3, 4, negative 7, multiply it by 0. It's a scalar multiple. 0, 0, 0 doesn't go anywhere. So if I'm asking you to move in a orthogonal direction, this doesn't help. Or if I ask you to move in a parallel direction, if I want a parallel line and I want to use a parallel slope to find that line, 0, 0, 0 does not create a line. It just sits there. It's a pretty boring vector. All right, and to finish this off, the angle between two vectors. This is a formula, okay? cosine of theta is u dot v, we just learned what the dot product is, over the absolute value of u times the absolute value of v. Now this is normal multiplication, okay? Because these are going to be numbers. We know how to get the absolute value. We use the Pythagorean theorem. This top one is the dot product. We're going to do an example, and then you'll get many more of these on the homework to practice. So here I have the vector 9, 2, and I have the vector 3, 4, and I want to find the angle between these two vectors. So I have conveniently placed both these vectors in standard position. I've put their tails together at the origin. Now I wish to measure this vector. So we take 3, 4 dot 9, 2 on top, and then we're going to have the absolute value of 3, 4 times the absolute value of 9, 2, and this goes on the bottom, and this is equal to the cosine of theta. Let's do a little bit of simplification here. 27, 8. 27 plus 8 is 35. So 35 is my numerator. Leave that up there for now. This becomes the square root of 3 squared plus 4 squared. This becomes the square root of 81 plus 4. Oops, sorry. 9 squared plus 2 squared, that's where that comes from. So here we have 9 plus 16 is the square root of 25. Here I have 81 plus 4, which is the square root of 85. And I know this is 5, but to simplify this, I'm going to call this 25 times 85 because it goes in the calculator a lot easier that way. So we're ready to use our calculator. We are looking for a cosine. So we're using cos inverse. My numerator was 35. My denominator is simply 25 times 85. And when I put that in my calculator, I will get my solution. I don't have my calculator up. Apologize for the delay. Should have planned ahead. All right, second quit clear. Second cosine 35 over second square root 25 times 85. Change that to an 8. 25 times 85, and we get 40 degrees. Okay, 40 degrees. And looking at our diagram, I certainly could believe that that's 40 degrees. Okay, this should be plenty of background for you to attempt some of the problems. Good luck.